Hello, and welcome to Chips Out Loud, a podcast series brought to you by Micron Technology. I'm your host, Jim Greene. In each episode, we'll discuss emerging technologies in the memory and storage space. We'll also focus on the customer needs that shape evolving modern client devices, as well as next-generation data centers. I'm excited to have Steve Pawlowski, Corporate Vice President, Advanced Memory Systems from Micron, here on the podcast today. Amid all the excitement of this year's supercomputing event now underway in Dallas, Steve joins us on the Chips Out Loud podcast to discuss some of the trends in high-performance computing. Steve, thanks for stopping by.
My pleasure.
Let's start with a little background, Steve. How long have you been associated with the HPC community?
Well, in my 4 decades in the industry, the first introduction I actually got into the HPC community was in 1992, when at the time I was working for Intel. And we were doing a new processor we called Pentium Pro. It was a large-scale out-of-order processor. And I was working on the bus cluster and the bus definition and the chipset developed associated with it. And it turned out, unbeknownst to me, that at the time we had a supercomputing division that was doing ASCII Red, which was the first teraflop system that was used by the Department of Energy to handle nuclear simulations. And so it turns out that chipset became part of what became the first teraflop system. So I got indoctrinated there because, of course, I needed to spend some time with the team in terms of how things worked. And, we did have some things we needed to fix. And just spent more and more time as I moved over to the labs with the HPC community. When I came to Micron, the reason for doing that was as we started focusing on the exascale compute problem, it was clear that the majority of the energy that these systems tend to consume are really on data movement, not necessarily in computing. And if you really try to break out the cost of, the different compute structures versus the cost of moving data in order to be able to do a single floating point operation, you spend about 100 times more energy doing the data movement than you do actually doing compute. And so the idea was, okay, instead of moving data to where the compute is, we're getting massive amounts of data, and we keep the data resident and do what we can to move the computing closer and closer to the data to improve the bandwidth so that we can improve the performance of these systems and to lower the energy so that we can improve the energy efficiency as well. So it's really kind of a two-pronged approach that we've been driving.
Mm-hmm. Well, how does that differ from traditional data centers? Do we take a different approach in terms of the relationship between memory and compute in an HPC environment versus a traditional data center?
Well, in some respects, we're focusing really at the compute memory complex right now, and then eventually we'll branch out. Traditional data centers have been based on an Ethernet backbone. And yes, you can build an HPC system and come up with the LINPACK number using standard high volume servers connected through Ethernet. Now, whether that becomes the most energy efficient way. And there are companies that have done that in the past, and their large complexes have been put into the top 500 list that is managed by the top500.org. So there's ways to do that. What HPC has really been trying to focus on is how they can get to deal with the complexity of large problems, whether they happen to be chemical problems, whether they happen to be material science problems, whether they happen to be, cosmic simulation problems, whatever it happens to be, and coming up with larger machines in order to be able to handle the complexity of, getting more data and trying to get greater accuracy on the results that we can as the amount of data that we get grows. If you look at the block diagram and you look at the hierarchy of the switches and the racks and everything else, it's kind of hard to tell the difference between them. It's the underlying technologies that really kind of separate out, how these machines really do look differently than just a standard data center.
You gave a couple of great examples, fluid simulations and cosmic simulations. Are they all intergalactic scale problems here? What are the typical workloads an HPC data center is going to be dealing with to have that kind of volume of data that you mentioned?
Well, there's those that really have very tight floating point requirements. So there are some like DGMEM and LINPACK, LINPACK's a benchmark, but DGMEM and then, other benchmarks, but they're really tight matrix where the amount of computation versus the data movement is fairly high. So effectively, you do whatever data movement you need, and then there's a significant amount of computation that would occur. There's that level problem. Then there are the conjugate gradient problems of sparse matrix vector multiplies and things of that nature, where it just tends to have the opposite effect of, needing more and more data movement per a given floating point operation. And there's a whole spectrum of different problems. There's the totally random that can be used for any type of graph analytics problem or, potentially random accesses, or things that are fairly localized. And like I said, there's a whole spectrum, and different machines perform better depending on what those programs do. And a good way to get just a brief summary of that is to go to the Top 500 website and look at the two major tracking benchmarks that they use. Actually, they have Graph 500 as well, but it's HPCG, high performance conjugate gradient workloads, and high performance LinPack. And the one number that you'll always see when they talk about the Top 500 machine is usually the HP LinPack number. That's roughly a small percentage, maybe 85, 90% of the peak floating point performance of the machine itself. And when you look at high performance conjugate gradient, the numbers tend to be a little less in terms of not being 80 to 85% of the machine, but maybe, on the order of sub 10% of the peak efficiency of the machine. And most of that is dominated by bandwidth, memory bandwidth, and effectively IO bandwidth. And so in order to get the machines to be more performant for that set of applications, that's where we've really been focusing on how do we improve the bandwidth to computation ratio that's existing in systems today.
Well, that's a good segue here, because I'd like you to share some views on a couple of technologies that I think stand to impact data centers of all kinds, and which are likely to get a lot of focus at the supercomputing show this year. Can you share your thoughts on CXL and DDR5 and HBM in terms of their ability to change that relationship between memory and IO and compute?
Well, CXL, for those of us in the industry, the way traditional processors have been, x86 processors have evolved is there used to be, when I talked about the machine that we built for ASCII Red, that actually was a shared memory machine, and it was a multi-processor shared memory machine where we had 4 processors sharing the same common memory interconnect. And so effectively, if you moved your application from processor 1 to, say, processor 4, it basically used the same memory and had the same memory access latency. So it was fairly consistent in terms of its performance and its behavior. What happened was, as we started to push more and more cores inside systems, and the cores were getting faster, that shared memory architecture became more of a bottleneck. And so, the processor vendors started adding memory controllers to the processor itself. Mm-hmm. And it really created the whole non-uniform memory access capability, where a processor talking to its local memory has a much different latency profile than having to go to memory on a different processor. And then with IO, there was a traditional IO bus, PCI, and there was a complex that was managed on the processor itself. So they were basically different animals, and PCI didn't have the concept of a memory and didn't have the concept of being a coprocessor interconnect where they could basically share the same system memory that you could on the CPU. The benefit of CXL is it reintroduces shared memory. And it reintroduces the concept of non-determinism, where with DDR memory, you make a request to the memory interface, and within a deterministic period of time, you have to have data coming back. You can't say, look, I'm not ready yet. Can we please stall? And so the benefit of CXL is it will allow us to put larger and larger pieces of memory out there, so we can actually start to build a larger subsystem of shared memory capabilities. When you look at ideas that HP had with the machine and others, where you have a large centralized memory, what we call disaggregated memory complex, where, all the compute agents have access to that large memory store, and they pretty much do through the same path, so you can democratize the latency across multiple nodes. That allows a certain set of applications to be able to take care of large shared memory problems. Not everything is a small distributed problem where there's fairly local and there's not interaction with anything else. In some cases, you really need those large memory pools. And so CXL allows us to get to larger and larger memory subsystems, and it allows us to bring new capabilities to the platform sooner than was available before. Because before, if, say, we had a new memory technology, and that new memory technology has some interesting attributes in terms of cost, interesting attributes in terms of persistency, But there are ways, we have to manage the media a little differently than we do with DRAM. And in order to be able to do that, there had to be a strong collaboration with the processor vendors to make sure those kinds of capabilities were into their platform. And then you're basically limited in terms of how you can bring those new technologies to market based on schedules of multiple vendors. With CXL, we have the ability to bring those technologies to market when they're ready to become available. And so it'll push the innovation on the platform from a technology point of view. In particular, when I look at some of the work that we're doing in some of the emerging memory effort, it'll allow us to bring emerging memories to the platform a lot sooner and be able to, create capabilities and new systems architectures that today traditionally have been very difficult to do in a really timely manner. So, CXL is a big focus for us because it does allow for more and greater democratization of the platform and for us to be able to innovate at the speed at which we can bring technologies to market as soon as possible.
So now we've got emerging memories that have arrived. Let's talk a little bit about DDR5 and HBM.
Well, DDR5 is continuing the tradition of the double data rate and technologies that have evolved over the last several years in terms of direct processor interconnect. And the focus here is on higher bandwidth, lower energy per data transfer. So it really is continuing to follow that same pattern of, trying to bring greater bandwidth to large multi-core systems because, as I'd mentioned on the conjugate gradient workloads, those processors are waiting for data, and if they can't get it, they'll make a request and there'll be a thread switch and it can potentially go work on something else, but they're waiting for data. And so DDR5's goal is to increase the bandwidth, to a pretty significant rate in order to help alleviate some of that data bottleneck and to reduce the energy so that we're not paying the same energy cost on a data transfer that we were with previous generation devices. And it allows us to leverage an ecosystem that the software is already tuned for, that the systems and the platforms have already been built for. So we're not forcing the ecosystem to change in a significant way. CXL will take some time to evolve because that's a different architecture and a different ecosystem. So DDR5 allows the systems to continue to improve as potentially there are opportunities for other changes to occur. That CXL could potentially provide. So DDR5 is extremely important in terms of not only HPC, but the entire IT computing system because it continues along that trend of high performance and lower energy.
Right.
And then finally, you mentioned HBM, high bandwidth memory. The idea of high bandwidth memory is really on the cusp of what I talked about earlier, which is how do you bring memory closer to the processor and take advantage of the extremely high bandwidths we can actually get out of the memory interfaces today, but reduce the cost of the energy of making that transfer. On memory systems today and on memory devices inside the part itself, we can easily conceive on a per die basis of having up to 1 to 2 to multiple terabytes per second of bandwidth out of that die. But eventually we have to push it into a standard interface and really not take advantage of that full bandwidth. And so the idea of high bandwidth memory and other concepts we're looking at is how can we take advantage of the fact that when you access a DRAM, you're bringing in a lot of data. For example, every access in a standard DRAM today brings in 2 kilobytes of data, so from the data and memory array into the sense amps. And if the access says, okay, I only need a byte of that, well, you just wasted the energy of reading all the rest of it. And so looking at ways that you can optimize by sending larger chunks of data and amortizing, your payload sizes are bigger so that you can amortize the energy of that initial access across the larger payload size. And take advantage of the fact that there's a lot of locality in those accesses, meaning that if the processor wants byte at address 0, it's likely it'll want byte at address, 1K at some point in the future. And we've done a lot of analysis at Micron on the different workloads to see if we did have, say, cache sizes on the order of 1K to 2K pages for what we would consider some pretty nasty workloads, not the totally random workloads, but workloads similar to the conjugate gradient workloads we talked about. If we had a cache that could handle that, the hit rates are actually pretty good. The problem is that now you're spending a whole lot of time fetching that data, but the hit rates are pretty good. So the idea of an HBM or a memory like that is have a large memory stack Keep it close to the processor so you're minimizing the length at which you're transferring data so you can minimize the energy. Take advantage of the high bandwidth inside the DRAM and transfer as much of the data payload when a request is made to the processor itself, and let the logic cache be able to handle, or let some level of caching be able to handle the fact that there's a certain locality in every program. In locality, meaning I'll bring it in and I know I'm going to use that data at some point in the future, either in time or either in space. And so take advantage of that and really try to push the efficiencies of these systems for those workloads that can deal with it. Now, the problem is as you bring that memory closer, you're trading off capacity for bandwidth, where with DDR5, you get very, very high capacity for less bandwidth. Mm-hmm. With HBM, you get really high bandwidth, but you're trading off the capacity. Mm-hmm. So systems have to be designed to kind of have that balance between when do I use HBM memory for the application, when do I use DDR5 memory, and eventually when will I use CXL memory in that whole mix.
Mm-hmm. Well, I think I can see where this is going, but I would like a final question to allow you to kind of tie this all together for me. If with you look into your crystal ball, how do you see HPC evolving in the future in, the next 5 to 10 years? And how is that infrastructure going to change to meet that vision?
Well, we've been doing a lot of work. I've spent a lot of time in the artificial neural net space. I did my graduate research on artificial neural nets. And so I've always been fascinated with the whole concept of, machine learning, artificial intelligence. And we've been spending a lot of time with some of our partners in the U.S. government looking at, AI for science. And there's an interesting diagram that was drawn quite a while ago that showed the difference between, as we're getting more and more data, how conventional algorithms, the accuracy of conventional algorithms has become somewhat asymptotic. So the more data you get, the algorithms don't necessarily get higher accuracy in terms of their results. But with AI, with more and more data, you actually can get a greater amount of accuracy in terms of the results that you're looking for. And so where we see this all tying together is getting larger and larger memory systems that have the larger data set sizes. But instead of them being located in a large storage array and having to swap in and out because of the limitations of the system, really being able to take advantage of these huge memory footprints and multiple ways for a processor to be able to, instead of having to go through several different types of interfaces, the application gets roughly the same latency to that data as it would regardless of where the process happens to be split up and going through. I actually see the opportunity for us to be able to leverage the best of both worlds, the knowledge of traditional science and the problems of traditional science, and the benefits that potentially large data sets with AI can have to get greater accuracy in terms of the results of those problems. Now, it's not going to solve everything, but I am starting to see where we're going to see systems that can do more than just look for, buying patterns and things like that, where we can really start to answer some of the fundamental problems we're looking at today in science. I have a research team working with the Health Sciences Institute here in Oregon, focusing on cancer research and being able to use machine learning to assist the physician in terms of identifying different structures and identifying cancers and potentially looking for ways that, drugs could impact, how drugs have impacted them before, and looking for, ways that we could potentially do something in terms of sneaking up on cancer, as they say, not that you're going to have this one cure that fits all, but a way to sneak up on them. And so that's where I see where high performance computing with these large memory systems and being able to leverage machine learning in a different way is really going to, fundamentally change how computing can help us in broader community. And traditionally, everything that was in these big machines eventually waterfalls down to mainstream IT systems in a 7 to 8 year time frame. And so that's where doing the work now in HPC guarantees that in the future we'll be able to see the technologies and the capabilities being available for the masses and have a big impact on society like it has today.
Yeah, it's big challenges, but again, the opportunity for big impact is really powerful. So, Steve, thanks for sharing. Thanks for joining us today. Our guest has been Steve Pawlowski, Corporate Vice President, Advanced Memory Systems here at Micron. So thanks for joining us, Steve.
Thank you. And I appreciate the time.
And thank you all for listening. You can check out the new technologies at www.micron.com. If you're at the supercomputing event, please come by and check out the latest and greatest from Micron. And you can engage with Micron technology on LinkedIn and in the Twitterverse. We'll catch you on the next episode of the Chips Out Loud podcast. you to our audience for joining. Please listen in again on the next episode of Chips Out Loud.